So here's what we're going to do. It turns out that it's sort of complicated to keep track of where all the maxes and the differences are and the absolutes and blah, blah, blah. So we're going to make a simplifying assumption, which is that the largest value in our f function is bigger than or equal to the largest value in our g function. And I'm going to say we're going to assume that without loss of generality. Why is that okay?
Because if it weren't true, we just swap f and g around.
Yeah, that's all. I mean, we'll just call f, of the two functions that we're comparing, call f the one that has the larger max.
Mm-hmm.
Or larger or equal. I guess if they're equal, if the maxes on the two are equal, then it doesn't matter. But we want f to have the larger of the two. And what that's going to do is going to simplify some of our thinking with the absolute value symbols, because otherwise the case analysis gets really tedious.
We can't have that. Okay. I can't wait to see where this goes.
All right. So ultimately, we're going to be trying to compare this quantity to this quantity. And so let's start off writing this quantity on the left, and then we're going to reduce it step by step until we get the quantity on the right. So here's where we start. What can we do with this? Well, given that we know that the max of f of a is bigger than the max of g of a, because that's what we were assuming when we named f and g, we can get rid of the absolute value signs. Yay! Now, because we're finally going to come clean on this issue that you were talking about before, which is that these are kind of different a's, and it would be good if we gave them different names. So let's actually do that. Let's actually say that A1 is argmax f of a, and A2 is argmax g of a.
Mm-hmm.
So now we can rewrite this difference, max a f of a minus max a g of a, much more simply, as just the difference between the corresponding values in the function.
Sure.
All right, so if you let me get away with that, now you're in trouble, because the next step is going to follow pretty easily from this, but it's going to take us into a whole new realm. So now we said that this quantity is equal to the difference at a1 of the f function and the value at a2 of the g function. So since this a2 was chosen to maximize the g function, then any other a that we could substitute in here, let's just say a1, can only make this smaller, or it can make it no bigger.
Right.
Right, so the GA2 versus GA1, GA1 is going to be smaller than or equal to GA2.
Yeah.
But since we're negating that in this equation, that means it can only make this quantity smaller than or equal to the previous quantity.
That's kind of amazing. That's a neat trick.
Right, so but it intuitively, like does this piece feel okay intuitively now? Essentially what we're doing is we're taking the place where f is maximized at a1 and the place where g is maximized at a2, and we're just sliding over to a number that's, well, here, think of it this way. So I find this little piece helpful. So because of our without loss of generality statement, we have that, if we think of this as a number line, we have the f value at a1 is the largest thing of all. It is the king.
Mm-hmm.
The g value of a2 is some other large value, but not as large as f of a1. So if we switch from GA2 to GA1, we have to be going down, or at least not up.
Mm-hmm.
And so if we look at the difference between these two quantities and the difference between these two quantities, the difference can only have gotten larger. And that's what this equation is showing, that the difference can only have gotten larger when we substitute in the A1.
Well, that's not true. It could stay the same. So f of a1, g of a2, and g of a1 could all be the same number. But g of a2 cannot be bigger than f of a1, and g of a1 cannot be bigger than g of a2.
Good.
No, that's really clever. So, I mean, this is cute. This gets you a way of going from two completely different variables to one variable.
Right.
That's awesome.